Okay, so I can start again? It's okay. So, welcome to the last session of VISGAP. In this session, we only have one last short paper talk, and then the invite is Capstone given by Sebastian Grottel. So, let us start out with Georgi Nonaka's talk about visualization on the K computer. Please.
Hello, everyone. Hello, everyone, and welcome to the talk from research topic to industrial practice. Today, I would like to talk a bit more about the experience that many of us are probably familiar with, and I would like to highlight certain things, certain aspects of it, and see how can we actually bridge those problems. So, what does research collaboration actually look like?
I am Georgi Nonaka from Riken Center for Computational Science, or RCCS, and in collaboration with my colleague Naohisa Sakamoto from Kobe University, we will talk about some observations and findings noted during the visualization software development for a supercomputer named K-computer. And here is the outline of this presentation, and I will start by briefly explaining the hardware and software environment and some factors that affected the software development, and will share some lessons learned. The K-computer is an already decommissioned system that provided computational resources to the users for a long 7 years. And as other supercomputers, it was a parallel system designed for large-scale simulations using tens of thousands of processors. And the Spark-based CPU was probably the main characteristic of that system. And the Riken RCCS was responsible for the operation of the entire facility and to provide computational resources to the authorized users. And here is an overview of the hardware and software environment. And Fujitsu co-developed the supercomputer and also provided the software set, which includes customized compilers, libraries, and tools optimized for the Spark CPU. And we have no complete statistics, but we could observe that different users have used different applications for the visualization and analysis of their simulation results, including open source as well as commercial software. And we also observed that traditional post-op visualization was done by moving the data to the local machines, or also by using auxiliary subsystem available to the users that include x86 and GPU systems. However, in this talk, we will focus on the in-situ visualization, where the total or partial visualization processing is done on the supercomputing side. And there was an officially provided visualization library from the Fujitsu for this purpose. And this visualization library implemented the particle-based volume render method without using OpenGL. Therefore, it did not require off-screen MESA library or OS MESA. And in addition, there was an API to enable integration with the simulation codes. And here are some examples shown in the Fujitsu web page. And regarding this particle-based rendering, we can also cite the remote visualization tool developed by the Japan Atomic Energy Agency, which uses the supercomputer for the part generation and a GPU-based client for interactive rendering. And from the user side, we could perceive different groups of users, and it is important to make clear that this is just an arbitrary grouping from our perspective, and we grouped as users who are looking for ready-to-use applications and can also pay for external service and support. And another group are a group of highly skilled users who are able to modify by their own, and we named as customizers. And we could observe the trial use of ray tracing-based Lux render, and also an effort to set up the OS MESA to use the ParaView and Visit for in-situ visualization, and in this case by using Catalyst and LibSim extensions. And there was also a small group of users from different fields who acted positively for collaboration, and we named as partners. And it includes domain experts from industrial and biomedical CFD, from computational climate and disaster prevention. And for them, one of the development results was a non-OpenGL application named Hive, which uses Lua script for representing visualization workflow, and used a ray tracing engine named Surface. And it was implemented by using OpenGL ES 2.0 compatible API, and also a GLSL ahead of time compilation mechanism to handle fragment shader codes. And for OpenGL-based applications, it is important to make clear that the Fujitsu compiler was only capable of building the legacy SWRAS driver, which provides only the fixed graphics pipeline capability. And although it was not only for the visualization purpose, we become able to pay for the external software porting service to increase the list of open source software for the K-computer users. And we acted as users, and in this list, it includes some compilers, and the most important for the visualization was the OS Mesa library, which include the LLVM pipe driver, which use the LLVM just-in-time compilation mechanism. And this LLVM pipe driver enlarged the options for co-development with partners. And as an example, we use the Kyoto Visualization System, or KVS, as the rendering engine for in-situ visualization of CFD simulations which uses irregular volume data, such as hexahedra and prism cells. And traditional render methods, such as isosurface and raycasting, as well as particle-based rendering, including the integrated object and image-based approach, have been also applied. And during this visualization software development, as some lessons learned, we can cite the importance of the available development tools, especially the OS Mesa library in the case of the supercomputer environment. And also the importance of working with partners for the code development and with their valuable feedbacks. And that is important to say also the trade-off for the hardware-specific optimizations, since some efforts can be in vain if there is no continuation of the hardware architecture. And for instance, the next supercomputer, which will substitute the K-computer, and its name is Fugaku, it's based on a totally different CPU architecture. It is an ARM-based Fujitsu A64FX. However, on the other hand, since we can expect a larger software development ecosystem, we hope that these difficulties will not repeat. And thank you for your attention.
Okay, thank you, Georgie, for this insight in this very particular system and ecosystem. So maybe to start off the questions, I was wondering myself, so basically this dual role, basically pretending to be a user and outsourcing something, that's not really a common experience for a visualization researcher, because usually we do not have funding to do something like this. I mean, it's of course a pretty interesting strategy, but what are your thoughts on this very special occasion, basically?
Yes, in the case of
Welcome to
that we acted as users was because we needed this library to develop visualization applications. So the users was needed to use the OpenGL library, but without the help of the hardware developer. Actually, when we outsourced it, we just asked for the hardware developer to port the OpenGL and other libraries, other compilers and other libraries that the user was wanting to use for our purpose. So we acted as a user to have these tools to develop these information applications, actually.
So basically your takeaway message would probably be that if you order some very specific hardware, it would be interesting to maybe have a more sophisticated software requirement list when you basically upgrade to another different, maybe even exotic hardware again, right? So you do not have to do it afterwards with other funding, maybe.
Yes. The problem was our system was so specific that the thing was the usual supercomputer acquisition is procurement based. So we define the hardware, software, the thing that we need. But in the K computer case was a development by a project. So it was a project based development. So the target and the goals was defined by the project group, and I believe that there was no visualization person in this group. So it was totally simulation centric system. So if we think the server that was put for the post processing was just an x86, there was only CPU and no GPU. So this shows what was the priority of the post-processing, the visualization for this project group. So as I said, for the next system, if someone that knows the value of this analysis and visualization part, probably it will be different in the next machine. And we hope that it will really occur, but we don't know.
Yeah.
What will happen.
I see. Thank you. I think there are no other questions. At least I cannot see any. So yeah, thank you again. Then we can basically switch over to the Capstone, which is presented by Sebastian Grottel. So as a short introduction, maybe Sebastian did his PhD with us in Stuttgart, and then he went for a brief time to Dresden as a postdoc. However, he could not really resist the beckoning of industry, and so he went to FARO not much later, which is in a way fortunate for us because now he can share basically the differences and similarities when looking at the same problem, which is developing software from the academic side and from the industry side. And so, without further ado, I'm happy to have you here. Let's see this capstone.
Talk on software sizes and intent in academia and industry. My name is Sebastian Grottel. I'm the manager of the software engineering department in the company FARO Scanner Production. I will present 2 case studies and a little bit of my own opinion on software development in these 2 worlds. But first I want to thank the organizers for this workshop to give me this opportunity to hold this capstone speech. And of course I want to thank all of you for attending my presentation. Let me start with some background about myself so that you know where I'm coming from. The most important time in my academic career was my time as researcher and PhD students in Tom Ertl's group in Stuttgart. I had a great opportunity to work in the Special Research Center SFB 716, funded by the German Research Foundation, DFG. Honestly, I don't know what was the official title of that thing anymore, but what we did, we researched a lot around large particle simulations. And in my sub-project, I researched interactive, real-time visualization of such datasets. And when I say such datasets, they originated from a lot of different fields of applications. So we needed a lot of different visualization styles, visualization methods to facilitate the needs of all those different researchers, for example, from thermodynamics, material science, biochemistry, and so on. And because of that need, we started to implement a visualization tool which I named MegaMol, and that tool grew a lot over the years and is even used today, and I will use that tool as the first case study in this talk. After 11 years at the universities, I joined the FARO scanner production in 2017. We understand ourselves as a measurement company. We produce measuring devices like terrestrial laser scanners and accompanying software to make sense out of the data. I joined as a senior software engineer and worked on the desktop product FARO Scene. To give you an estimate of how big this software is, we're talking about 21,000 users worldwide. That is not your Facebook size or anything like Google, but nevertheless, if you introduce a bug, a lot of people will be angry at you. And after being a team lead for the visualization group, I'm now the manager of the software engineering at the FARO scanner production company, meaning I'm responsible for 2 products now, not only FARO Scene, but also FARO Scene WebShare Cloud, which you can see in the lower image, our cloud product to share the final data results after processing within Scene. This brings another 400 customers and another 30,000 users to the table. Again, not big, but big enough. I will use FARO Scene as my second case study example, and comparing it to MegaMol will give us some insight on the different world of software engineering and software development. But actually, these 2 worlds aren't that different at all. In the end, it's programming, and programming it's easy. The hard part is maintaining a stable software and growing a large software. And that's exactly the point. The larger the software, the more complicated that stuff gets. That's why size in the software does matter. But not all problems need large software. A lot of problems are perfectly fine to be solved with a small program. And that's now the interesting aspect. When do we need large software? When do we want to do large software? What is our intent when developing software? What are we want to do? So this intent differs between academia and industry, and this is the main difference I want to highlight with the 2 case studies as the examples MegaMol and FARO Scene. And following the workshop's title, I do not only want to highlight the differences, but also the gap between and how we can combine this, how we can bring academia software and industry software closer together to collaborate and to benefit from each other. I believe this transition is not that complicated. It just needs a simple tooling. It needs modularization, some polishing, some modularization, sharing the components, some modularization, the integration of the algorithms, and some modularization. So after the case studies, I want to share with you, let's call it my opinion on how we could close the gap, what we could do to bring academia and industry closer together. But first, I want to talk a little bit in more detail about my argument on software sizes, why they do matter, and how we choose the right software size for the right problem. Then we go to the case studies, and I will finish with my opinion on what we can do to bring academia and industry closer together. I use a very simple scale for software size here. So ranging from a program, which is just a small, very precisely focused piece of software aiming at exactly solving one task, one problem, over applications which are mid-range sized with a focused range on specific topics, multiple topics, but all in the same direction, towards larger systems, which are flexible in focus and can do a lot of different things. Your typical program would be, for example, the Linux tools, or something as simple as FFmpeg, doing exactly one thing, but doing that one thing good. And for example, the proof of concept prototypes you often write for research papers, that's exactly this category. Applications are wider. So, for example, Excel, the universe's most important software, that's an application. It has its focus on table-based data, but it can do a lot of different things here, like analyzing, communication, showing diagrams, and whatever you need, it's there. Systems are even more generic. So, for example, the robot operating system for controlling a robot, but nevertheless, it could be a robotic arm, it could be a mobile robot, it could be your favorite vacuum cleaning robot. Still, it's focused on something like robotics, but very flexible and wide and adjustable to the problem you're currently facing. That is a continuous scale here. These are not 3 different and distinct categories. A program might be a small application. A larger application might be a system. So please understand that scale as continuous. But continuous and non-linear. Excuse me for using this management-like diagram here without any units on the axis or something like that. Well, I am a manager. The point I want to make is the non-linearity. The larger a software gets, the more issues it can resolve are in its focus, the more functionality you have, but also more code complexity is introduced, and that increases the development effort and the maintenance effort, and if not done correctly, that can get arbitrarily bad. So if you're focusing at a large software, a large application, or even a system, you must be aware of that you will need to invest a lot of effort into the development, into the maintenance, to do it right, to do it in a sustainable way. As I said, if you're aiming at a large software, for many problems, you don't want to go there. And that brings us to the intent. What do you want to solve with your software? In academia, most of the time, it's a proof of concept implementation of your research, or it's a foundation implementation to facilitate more advanced research. So most of the time you will be at the lower end of the scale, producing programs for proof of concepts or small to mid-sized applications to be those foundations. And that makes sense. You only invest as much effort as you need to reach your goal. Systems are almost never needed there, so there is no need to invest so much effort there. In software industry, I have a different intent. I want to support my user. Okay, cynic people would say, I want to sell software, I want to make money. And of course there's truth to that. But what I really want to do is I want to support my users in their workflows. I want to create value for them. And that value is exactly what I ask them to pay me for. Bottom line is, I want my users to want to use my software. I don't want to force them. And that is best done by offering the value they need. And now there is a question of optimization here. Where can I generate the biggest value for my customers with the least effort I have to invest? It seems that there is some sort of a sweet spot for applications. Applications are powerful, so they bring a lot of value for my users, and applications are okay in the effort I have to invest to build them. So there is some sort of a focus. That focus, of course, shifts to the right, because the more powerful an application is, the more valuable it is to my user. Over the time, all the applications will grow larger, and every application which is available on the market for some time will have a lot of effort. Additionally, there is also this trend towards systems to provide even more capabilities for the user, to interconnect multiple applications, to keep the user in the ecosystem, to optimize their workflows, and of course, to own the user. So here's the difference in intent. While academia focuses on the lower end with programs and small applications, industry focuses on larger applications and systems, thus on the larger end of the scale. And, as I said before, this makes sense. In industry, I do want to have the larger software to fulfill the needs of my customer. And customers always ask for everything. Give them a text editor, and they will ask, where is the video playback support? So even if you start with a small application, those things will grow. Whereas most of the time in academia, a proof of concept prototype is all you need. And let's face it, software in academia most of the time lives exactly as long as the corresponding PhD student is part of your group. Of course, I do know about the long-term research projects and the software packages they develop, but those are exceptions. But even the programs the PhD students write, even those grow during the time he's researching. And even more so if a research focus is spread over multiple PhD students sharing the same codebase. To give you an example from my past, there is this research paper about point-based rendering of galactic dark matter simulation data, which is point-based rendering. Then there's a second idea. We can do GPU-based glyph ellipsoid raycasting to show tensor field data. It's also point-based data, so let's use the same source code. And suddenly the program grew in complexity. Then we have these thermodynamics researchers doing these complex simulations with dipole molecules. Let's create GPU accelerated glyphs for them as well. Again, particle data, it's sort of point-based. Let's use the same source code. Works out fine. Perfect. So far, so good. Since you only need measurements, screenshots, and videos, you don't have to worry about maintenance. So all's fine. Until your research group leader comes to the idea, well, we are experts in point-based visualization. Let's do this huge research project with millions of researchers and different applications and bring everything together and solve all visualization needs for everything and everyone. We already have the source code for that, right? And now you're screwed. Now you have to make do with programs to solve a problem of a large-scale application. And that not so hypothetical example is exactly the reason why I started writing MegaMol, an application to be modular to bring all those needs together. But the history is not only those 3 papers. So here is a short timeline with a selection of other papers, all based on the same source code. So we have the point-based rendering, we have glyph raycasting, we have even tubelet raycasting, which is basically just connected glyphs. We have data visualization with some diagrams, fancy stuff, and all is in the same source code. Yes, that is possible, but obviously, that is not maintainable, that is not sustainable as a software to be used in a longer running research project. And this special research center SFB 716, which started, that was for 4 years with the outlook of having 2 extensions by each 4 years, so a project which could exist for full 12 years. And spoiler, it did exist for the full 12 years. And even more, the system MegaMol is even used still today. So by the way, the name MegaMol came from the idea of interactively visualizing millions of molecules. So what I had to do now is to take this software, these programs with their organically grown anti-structure and make sense out of that and make something which can act as a basis for our future research, as a foundation, with a modular toolset to support our future research. On top of that, since in the Special Research Center we were collaborating with different researchers from different fields, I also wanted the tool to be easy usable so everyone could use it. I could give it to the material scientists and the thermodynamicists and say, play with it, try it out, come up with ideas to create a positive environment where we benefit from each other by generating insight, generating ideas, generating process, and therefore, of course, generating science. So from the introduction slide, you might have noticed I'm a big fan of modularization, and that is the approach I took here. The idea of the basic architecture of MegaMol is having a core with a framework with all the management and utility functionality you need to have this software up and running, to use a plugin mechanism to isolate specific research functions, and to have a front end for the presentation layer towards the user, also including a user interface, a simplified user interface, only adjusting parameters for the visualization. And that approach worked out pretty well. So basically what you had is the shared core, a shared front end, and a plugin for each PhD. So everyone could work on their own, isolated, do whatever they like, and in the end, everything together worked as an application. Of course, this is an oversimplified view. It did not work without problems. As every software, MegaMol has problems. But I believe the fundamental idea was proven to be working. On a more detailed level, the functionality within MegaMol is also broken up into what I called modules and interconnecting calls. So we had a module for just viewing a 3D scene, basically managing a 3D camera. Then we had, for example, a simple sphere renderer, which is sphere glyph raycasting in OpenGL, which can be shared as long as the input data is the same. And on the right hand, we have a data provider, loading data from files or connecting to a simulation. Now, I made one design decision here. That is the direction of the arrows. I designed to configure and to model control flow, basically the direction of function calls, and not the direction of data flow. This is often a little bit difficult for visualization researchers who are often thinking in the direction of the data flow. That might have been a bad design decision, but it worked out in the end, so it's okay. I mean, it allowed us to create module graphs and functionality like this one, which creates a complex combined visualization of glyphs, of volumes, of isosurfaces, all on the fly derived from the original input data. And that is, let's face it, somehow it's cool. You might not like my choice of color map in that example, but being a PhD student, working with a complex data, a complex algorithm, throwing everything together and ending up with this, and knowing, well, I did everything here. I added complexity as I go along, and I know that the complexity of my source code has not grown dramatically because it's just side by side different functionality. For me, as a software engineer, that was satisfying. And it still is if I look at those pictures and know what's behind them. And that's just one example. Over the years, we added a lot of different visualizations, maybe the most complex ones for biochemistry shown on the right, even including specialized front ends for specific applications, and all that based on the same foundation, and all that without jeopardizing the maintainability of that foundation. A personal highlight was our entry in the SciVis contest in 2016, where we created this specialized front end for data analysis based on a tabular view, on graph views, and integrating the original 3D point data visualization with different color coding and shading. And we created a system, something which really helped to delve into the data, getting an overview and drilling down to the details. So I had my share with software engineering and software development in academia. When I then moved to the industry and then was facing this huge blob of scene source code, that is still a different kind of beast. First, what is Scene? Scene is a desktop application. Its focus is on processing, editing, cleaning, converting data, 3D point cloud data from our laser scanners, inspecting what you get, and in the end somehow exporting the data for further use in other applications. A typical workflow would be to scan a site, a factory or something like that, with a laser scanner and do like tens or hundreds of scans. Big projects do thousands of scans. Each scan containing a lot of points, millions of points, and then you bring everything together. You process the scans, you filter, you clean up outliers manually, and then you do what we call register the scans, bringing everything into a common coordinate system to set up a project from the local individual data. Then you start inspecting that project and derive information like measurements, distances, or create images, videos, some modeling, export the data in whatever format you need as your final deliverable. This is a video of a scan project we did within R&D to test a new scanner generation. We went to the German town of Dischingen to scan this nice church from the inside and from the outside, and actually, while we were at it, we also scanned the rest of the town around it. We followed the workflow, cleaning up the data, combining the data into the project point clouds, and this is the result. And it's a nice result. You can view the church from the outside, from the inside. You have those amazing details from directly under the roof, showing the precision of our laser scanners. And of course you have the centerpiece, the inside of the church, with all the detail. Remember, these are no videos, this is not the photo, this is the point cloud we recorded, this is just colored points. So what's the intent of writing a software as seen? As I said, we want to improve the customer's workflow. We want to create a value for the customer, which is more valuable than the price point we ask for this software product. As we work with large data, performance and efficiency is important. These data sizes are huge. A typical project is hundreds of gigabytes, tens of terabytes in size. So we don't want to convert any data, and all the operations a user has to do should run fast. Then of course it's an end user software, so the effectiveness is important. The software has to work under all circumstances, and that's not just all the different computer hardware, it's also the different input formats from the different scanner generations or even scanner types. So like combining laser scan data with data from photogrammetry or something like that, everything has to work. And most importantly, I told you we understand ourselves as a measurement company, so the user must trust us in the correctness of the data. If we say a distance is a meter, so-and-so centimeters, and so-and-so microns, that has to be correct. With this intent, I hope you believe me that the scene software itself is complex, is difficult, and that it took some time to write it down. And it did. Scene is 19 years old. I mean, the initial commit is 19 years old. Most likely Scene was already in development for some time at that point. With 19 years, Scene is an old software. And it has its quirks, it has its strange parts, but for good reasons. And to understand those reasons, you need to understand where it comes from. Originally, Scene was the controlling software for the first scanners. Those scanners did not have onboard computers of any kind, so a computer with running Scene was the direct controlling software. So there was a real-time and hardware interface aspect to the software. Also, keep in mind, 2001, for the first commit, a lot of convenience functionality we nowadays have in C++ didn't exist at that time. So Scene needed to create a lot of base types and base classes, which kind of seems strange today. Of course, over the time, the scanners grew more and more competent. They got their onboard computers, SD card storage, battery packs to work entirely wireless. So there was no longer a need to directly connect to Scene. At that point, Scene separated to become a post-recording and processing software and software for inspection of the data. But with this constant change of scanners and evolution of scanners, of course, Scene had also to adapt. Scene needed to learn to load the different file formats from the different scanners, even different scanners types. So we do not only have the laser scanners, but also structured light scanners integrated. This, of course, brought in a huge growth of complexity to the software. And at the same time, having only a small team of developers at that point in time, the complexity could not be answered by the needed refactoring of the source code. So, as with every larger software, a lot of the source code seems outdated, redundant. But keep in mind, it's legacy source code, so it's not necessarily a negative thing. It still has its value. It has established, it works, it has proven itself for 19 years. But developing a software for 19 years comes with its drawbacks. So we have a rather large Git repository, and that is not because of any binary artifacts or anything. We have basically every programming language in there you can imagine. The source code itself is roughly 6.5 million lines of code. And that's not your average code, that's really complex stuff in there. And even worse, since the software used to be the controlling software for the scanner, Scene is now used, or the Scene source code is now used by 4 independent development groups from the same repository. Just As an example, it's the group developing the scene desktop application and the group developing the firmware for the FARO laser scanner. Some of these teams are rather small, and so conflicts and difficulties during this combined development on the same source code exist. Of course, they do. But there are also a lot of benefits here. For example, tooling or even testing and stuff like that. One group does it, all the other groups benefit from it directly. And we do our best to fight the difficulties, to fight the complications by introducing cross-group teams to work on specific topics, and of course by driving modularization to isolate the different aspects of the software. So talking about modularization, Scene exists of roughly 90 libraries, components, projects, whatever you want to call it, and has further dependencies to 150 external libraries. And that's only internally for Scene itself. In addition, Scene also has an API, allowing third-party vendors to create plugin apps to introduce into Scene and to import functionality into Scene to extend what we can do within our software. The same API can be used the other way around to integrate Scene into a third-party application to be used as an engine or example for the point cloud rendering, or to utilize the file format import-export capabilities. While I am a big fan of that external modularization and that API providing these possibilities for integration in both directions, this comes at a cost. The maintenance effort for an API is significant. You need a versioning concept, you're freezing interfacing, limiting capabilities of correcting bugs and introducing new functionality. And if you have to give support for the external developers, that's often not trivial, because the software itself is not trivial and the problems cannot be reproduced by minimal working examples, so you oftentimes face huge debugging problems. As soon as you work with different developers from different groups, or even worse, from different companies, an ABI, an application binary interface, is necessary. You will die without it. And that is difficult because breaking an API is very, very simple. So, additional effort here as well. And the biggest problem now is how to convince your stakeholders that it is worth to invest into that API. They will ask you, what's the benefit? And you can only say, I don't know, it's indirect, it's for the future, it's for our partners. And it's very hard to get fixed numbers on that. Nevertheless, if you're aiming at a larger application or a system, it is worth the effort, especially if you want to collaborate with external partners which are not inside your own company. This is all about software modularization, and software modularization is about isolating concerns and isolating responsibilities. Now, although I believe this is a very, 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 very important topic here, the modularization, I don't want to invest too much time here. It's an old story. You all know about it. Everyone does it. Everyone knows about it. Truth is, no, they don't. It's so simple. You know all these proverbs. Divide and conquer, separation of concerns, keep it simple and stupid, and so on. But oftentimes, a lot of people think, I don't need that now. I can introduce that later. And that is the root cause for all failure in modularization. Of course, there is the KISS principle. Keep a software as simple, as small as possible. And that seems conflicting with the idea of modularization, where all the time some idea of overhead is in the room. Actually, it isn't. It's just a question of how much modularization and where to do the modularization. Based on my experience, I recommend to always do a certain amount of modularization, at least in the terms of a separation of concerns. So even in a small program, try to separate the data from the algorithms. Don't intermix. Try to separate the application logic. Try to separate the presentation layer and the rendering. Try to separate file I/O. If you mix those different topics in, for example, one class, that is not a good idea. And separating those into individual class does not really introduce a lot of overhead. So my recommendation clearly is do that. Separate by functionality terms, and then separate further by concerns, for example by different data types or something like that. Keep your interfaces clean and simple. Minimize what you have there. Minimize complexity, minimize dependencies. Minimizing dependencies also means avoid deep dependency trees, because those will be a maintenance burden if you ever have to go into maintenance. Following those recommendations will not introduce a lot of overhead during development, and they will allow you, if at some point your program evolves into an application, to separate, to collect, to modularize, to recompose your software as you go. And this internal separation is basically always useful. Always do it. Whereas the high-level modularization, like runtime composition of functionality, plugin interfaces, plugin systems, most of the time you don't need them. Most of the time it's over-engineering to introduce it. You can go a long way to really big applications without those. So only introduce those if you're sure you need them. So let's assume you have that software, you have that modularization, you have a brilliant algorithm, and you now want to bring it into the industry. What is needed to go there? You have all the technical stuff in check. What else is needed? And that is what I call the non-technical interfaces. That is what needs to be done correctly to interface academia and industry to seal the deal, to make it happen, to make the transition happen for your new algorithm. Let me clarify the definitions here. So you have your implementation, that is your algorithm, your data structures, your programming language, etc. You have your interfaces, which is the functions, declarations, exchange data structures, and file formats. All that technical stuff, trust me, is not a problem. It might be a complication, but is always solvable. The problem I call the non-technical interfaces, that are the showstoppers, which will bring the industry to ignore what you did, even if your algorithm is brilliant. As an overview, you need to make it easy for the industry to trust your new implementation, and for that you need a reference implementation and documentation. This will make your case how valuable your software is. Now the question is the cost. How much effort is needed to integrate your algorithm into our application? And for that, we need interoperability information. And last but not least, I need to understand the maintenance and development process. It's about the people, about the developers behind the software, not about the software itself. The most brilliant algorithm is worthless if I know bugs will never get fixed. Let's look at those points in detail. Basically, I'm willing to invest effort to get an algorithm into my application. I'm even willing to re-implement the whole thing. But what I need to know is if it's worth the effort. So I need to know the value, the benefit, and the effort. To make your case for the value, the best thing is to provide a reference implementation which can just be tried out, which can just be used up front to see what your algorithm does to the data. And for the effort, a lot of things have to be understood. For example, the complexity, limitations. For example, would your algorithm work with the generated data? And then, of course, there's the question how to integrate everything together. The interoperability with the application is the first thing which comes to mind. Interestingly enough, the application itself, the structure of the application, is not necessarily defined by the developers. It is defined by the workflow of the users. It's defined by the intent we try to solve with the software. So the application follows that workflow, and all modules to be integrated need to follow that structure of the application. Remember the example from MegaMol, where the module graph follows function calls and models a control flow instead of a data flow. Now imagine you created a module which works on a data flow concept for connectivity. Those two worlds, to bring them together in a single application, is additional effort, and that is one of the efforts I want to understand before I start integrating an algorithm. Then there's the data. Most importantly, the data lifecycle. Who owns a piece of data in the main memory? Who is responsible for loading and unloading? If we talk about large data, then additional questions arise. So for example, how can we avoid data conversions? How can we avoid copies wherever possible? At some points, we want to have copies for isolation of concerns. At others, we won't. For even larger data, we have to consider out-of-memory scenarios. Think about the main memory is always too slow. How can we work out of core? How can we work with batch processing, parallelizing, or streaming interfaces? Don't misunderstand me. I'm not telling you that every single small research prototype should consider all those things. What I do have to understand as an industry programmer interested in adopting an algorithm from academia is how those things were considered or weren't considered. If they weren't, it's not a big deal. Then maybe I just need to do a re-implementation. But what I have to understand is I need to know that up front so that I correctly can estimate the effort to integrate your algorithm. And then there's the question of the delivery complexity. It may sound simple, but actually that is a huge pain if done incorrectly. So, do we have binary compatibility for partial updates? Artifact size does matter. Consider continuous delivery. Consider your application is updated every week and pushed out to the customers every week. And that is a scenario which is more and more important in the B2B business. So if I have to upload a terabyte of data every day, every week or whatever, it gets a pain and you don't want to go there. But it's not only the size. More importantly, it's the dependencies. More precisely, the dependency graph over your whole application. Ideally, every application or every dependency should end up at the same version. In reality, they never do. And I'm not talking about the Windows typical DLL hell. That is a problem. It really is. It exists. But I'm talking about the simpler stuff, like if I do not want to compile everything, and I do not want to compile everything, I have to consider how to isolate dependencies in different versions in different aspects of the software. For cloud applications, nowadays you just use Docker. You isolate every part, every microservice into specific portions, into specific Docker abstractions, and you're sort of good. I honestly don't know if that approach or a similar approach works for desktop applications. I'm sort of reluctant to deploy semi-virtualization containers for a simple application which should run in a single process if done right. I'm more on the side I want to do it right, but we will see if that works out. And that brings me now to the last and maybe most important non-technical interface. It's somehow related to the overall intent of what I want to do with my software. I also have a specific intent of why I want to use your algorithm and for what I want to use your algorithm. If it's a small and isolated focus, everything shouldn't be a problem. Most of the times, however, I want to have an integration into my application and I want to use it for a long term in a complex scenario. And as I said on my very first slides, developing programming is easy. Maintenance of software is hard, and I do not want to introduce a maintenance hell into my application if I can avoid it. And one aspect of the maintenance is, of course, changing the software, introducing new features, further developing it, and of course, fixing bugs. If I consider to integrate an external source code into my application, the question is, do I also want to take over the maintenance, or do I trust that an external team takes over the maintenance? And the second option, of course, is the far more attractive one. But who is that external team? As I told you earlier, a single PhD is not a team. A single PhD will finish his job at the university, will leave the university, and then the accompanying software is doomed to die. As an industry, I will not use that software. I might hire the PhD, but I will not use the software on its own. So if our goal is that I, the industry, integrate your algorithm, your software, deeply into my software for a long time, the best option is that you can provide me with a development and maintenance plan, that you openly communicate how long do you think this software will live. In the best case, you have the team to cover the maintenance and the further future development. A perfect scenario is open source. Create an open source community of multiple people dedicating to further development and maintenance of the software, and trust is guaranteed from the industry side. Whatever you do, you have to be clear in the communication. Let me conclude with a summary. The tooling, the processes, the standards, the methods, everything is already similar between academia and industry, if done correctly. Hacking exists on both sides. The difference is in the intent of the software. What do we want to do with it and why? Academia software is valuable for its creativity and the big advancements in the algorithms. The focus is on the development. You provide value. And if you want to have the industry being interested in that value, it has to be larger than the effort needed for integration. The industry aims at sustainability and trustworthiness. The maintenance is our focus. We need a stable software which exists for a long time. So in both worlds we have both aspects of the software engineering. We have the development and the maintenance, meaning we can bring those two worlds together. While academia can be the creative development, industry can be the provider for a stable foundation, for a framework. This conflicts, of course, with traditional ideas of commercialization of software. And a change of mindsets is needed here. And I'm not talking about making something like FARO open source and freeware and change our business model. Far from it. But using the right business cases, we can provide a software foundation shared among our product and open source projects. So in my opinion, bottom line, we need to close the gap between the visualization research and the industry software from both sides. We need the industry to open up to the universities, and actually I'm working on that. And we need the universities to close in to the industry by delivering the non-technical interface requirements, by building trust and providing an easier to integrate software solution. Closing that gap will not be easy. It's a long way ahead of both of us, for both of our worlds, but I honestly believe it's worth the effort. And I honestly believe we need to do that, we should do that. And workshops like this are definitely steps into the right direction. And so I reached the end of my talk. Thank you very much for your attention. And now, of course, I'm happy to answer all your questions. Thank you.
Okay. So thank you, Sebastian, for your insight and for your nice talk. We already have accumulated a couple of questions, so I think it's probably easiest to start with a simple comment. I'm just going to read this for posterity. That people liked your formulation of organically grown anti-structure programs, which of course is kind of a statement what happens if you let software grow too long unattended. So yeah, I'll just go to the questions top down. So the first was from Petra. Where do you see basically the intersection between academia and industry with regard to these program application system terms that you introduced?
First to the comment, I also really liked this in a previous talk, the formulation of tumor-driven software development, and I believe that's exactly the same thing. That's happening. We all see this. So yeah, we agree on that. Now for these software sizes, the intersection, I believe, is over the whole board. Basically, industry and academia use the same scale and the same types of software. We just use the software for different purposes, and therefore, naturally, the software or the sizes of the software we produce are on different positions on that scale. But the longer software lives, the more it will move to the right, the more the software will grow in complexity and sheer size. I think we don't even have to search for an intersection here, because it's the same living space for both worlds. What we need to have is, beyond that scale, a mechanism to bring the two instances or multiple instances of the different software packages together by showing, as these software grow to the right side of the scale, that we do not create too many application and system monstrosities in parallel, but that we try to focus and consolidate on common platforms and common systems.
Okay. Yeah, that's also something we have been thinking about for quite some time, but there still does not seem to be a solution that everybody agrees on coming around. I mean, that is basically the problem overall. But yeah, maybe on to the next question, because we have a bit of time, but not too much. Are there also design decisions that came back to haunt you later? That's something that Martin was asking. If so, how did you attack those ghosts of the past?
The official statement is no. My design was flawless from the beginning. The reality is, of course, there are a lot of design decisions which came back to haunt me. There are a lot of technical details where I thought, basically the moment they were pushed into the repository, I thought, oh, well, that might not have been a good idea, and yes, it came back. And it was not a good idea. Now, how I handled those, that's very easy. I left the university, and I handed over the whole software package of MegaMol actually to Guido, our session chair here, and now it's his problem. And actually, to my understanding, he has 2, 3, 4 PhDs, and actually also a technical programmer taking care of that and rewriting parts of this software. I mean, a software of that size and of that age needs at least partial rewrites, one and now. And that's exactly what they're doing now. We learn from the past. We learn especially what was good, what was bad, and the things that were bad need to be replaced.
Yeah, actually, the interesting thing here is that the parts of MegaMol that are the biggest problems for us currently are those parts where you had to skip over modularization to get something shipping at all. And so basically this proves the truth in your whole talk, because that's the things that we need to re-engineer at the moment. And that is going to be a lot of work still for quite some time.
You're welcome.
Yeah, thank you, yeah. I think Christina was asking, how do you measure value to the customer?
Yeah, good question. We have specialists for this. So we have, from the business side, marketing, project marketeer specialists, however they are called, I don't know. And what they do actually, they analyze the workflows of the customers, they analyze the markets, and then they see where are the pain points, and how does our software and software of competitors address those pain points. And then let's also compare it to, from that, it creates a value matrix with perceived value. So basically fixing functionality for the user and price point of the different software packages. And you create a value to cost landscape with all the different applications in there to analyze where you are. And this is very much a business process, but it's very similar to what we do, for example, when we write application papers. We talk to the domain scientists, we understand their pain points, and we create solutions exactly for those pain points. Where there's no problem, we don't have to invest time for the software. And it's basically the same thing. It's just an analysis on a different scale and on a different databases.
I think now we have two questions that seem partly related. So one is from Christina. So how open do you think companies are in general in terms of getting suggestions from researchers on how to extend your software? So that is basically the one part. And the other part is regarding your statement that you would hire a PhD but not use code if there was no maintenance. Because this reveals a problem where academia and industry are basically in direct competition regarding capabilities and resources.
Yes, and I mean, we are in direct competition about resources. There is no way of formulating that in a nice way. I have not enough programmers to do the jobs. I don't have enough developers to solve all the problems we're facing or to implement all the great ideas we have and we found from you guys. So it is simply a lack of resource. And by the way, FARO is hiring. So if you're fed up with the university, just reach out to me. In the end, it comes down to priorities. In the end, since I know I won't be able to implement everything to resolve all the problems, I will just attack the most important ones. The ones where I can create the biggest value for our customers with the least effort. And that's basically exactly the point. To identify those opportunities, that's the difficult part, and that is where what I try to show with my non-technical interfaces. If from the side of the academia, the information is provided that I can easily judge the complexity and the cost of bringing a solution into software, then I know what I'm dealing with, and then I can estimate how big will the gain be. Is it, in the end, does it make sense to do it? And if so, yes. And the statement with the PhD, of course, I mean, it's true. I will hire a good PhD. I will hire a good programmer anytime. Of course, I need good PhDs also to be in the industry, in academia. Especially, also we need good postdocs in the academia to keep the machine running. And what I can only hope is that we have some sort of a self-adjusting system between the industry and the academia here, at least with good environments created by the politics and politicians and governmental supports for academia. I hope that both worlds will continue to live on healthy, and that we can bring the collaboration in front, collaboration into existence, combining both worlds here. So I do not want to steal promising future researchers. This statement was more focused on the aspect that I will not use a software or software component from which I already am almost sure it will die in the maintenance phase. As I stated in my talk, the maintenance, that's the thing which basically is the highest cost during the software life cycle. So that's why we have to be very cautious at that end.
Yeah, something came up just now, which is interesting enough that I think we should just squeeze this in. So Peter was saying, what drives industry to fund PhD positions, and what are expectations from your side for that? Because that's something that exists, but it's extremely rare.
Yes, it is extremely rare. Basically, it's the same story of what I told about having my software development stakeholders to approve developing something like an API, something which only derives or brings in indirect value. And in the end, I think the crucial aspect here is the people. It's not so much the specific research problem, resolving exactly that problem we fought for decades or anything. It's about the people. It's about creating relationships between the management area of a company and the management area of a research chair of an institution. If we start to see the similarities, if we start to talk to each other, we will come up with ideas for project collaborations. That will happen. That will happen. And as soon as we see this project starting up, and that's for me would be the entrance gateway to create collaboration projects with partial funding from some research foundations and industry come together first to build up the connectivity between the people, the connections between the people. And when this works, when we see that value is created from such a project, this opens the door for larger funding from the industry point of view. Especially if you see what's happening, that, for example, larger companies really take a huge blob of money, give it to the academia and say, okay, these are 2 PhDs and 1 junior professor, whatever. This happens not overnight. That is not a start project. That is the result of a longer standing collaboration. And that is what we have to establish.
Okay, thank you. I think we need to stop here. There's one question left, but it's rather technical. I think it's easier if you do this basically one-on-one later on. So thank you again for this capstone, and I would now pass the word to Michael so that he can conclude the workshop and everything else.
Thank you.
Thanks for being here.
Yeah, thank you. So it's my turn to conclude this exciting workshop. And we have prepared a couple of slides for this. Okay. So, yeah, already full day workshop is over. My name, as Guido just said, is Michael Krone. And on behalf of all my co-organizers, let me quickly summarize what VISGAP 2020 was about, what was happening here. So we had 2 very insightful and I think exciting invited talks here. The keynote by Julian in the morning, and Capstone by Sebastian just now. We had 10 exciting paper talks and with joint discussions at the end of the sessions with all authors. And even though the virtual format makes discussion maybe a little bit more difficult, we were, I think we had really lively discussions and interesting ones and a lot of interesting questions. And we were also quite happy with the attendance, and we were frankly a bit surprised by the number of participants. So at times we had more than 100 people watching the streams, which we think shows that there is great interest in this topic of closing this gap between the 2 worlds, software development and research. But of course, as we have also seen, this problem is not yet solved, which actually leads me to an outlook. So what's next? What's going to happen in the future? And for this, we would very much like to hear your feedback. How did you like the workshop? How did you like the topics, the selection of topics? How was the length? Was full day good? Would you have liked half day better? Were the joint discussions good? So whatever comes to your mind, please let us know either on the Discord channel during the week. You can also send us an email. You have our email address here and on the website, and you can also participate on Reddit. So there is a Eurographics Reddit here where you can also continue the discussion. Where we would also like to continue the discussion is a Dark Stuhl seminar. So we are planning to submit a proposal for one. And of course, we would also like to hear your ideas on that. And maybe even if you want to, you can write us some topics, some related topics that should be discussed here, should be included. As Christina mentioned in the opening, we already organized a Shonan seminar about this topic last year. So maybe in the future, we might also think about submitting a proposal for another NII Shonan seminar, because we are really enthusiastic about this topic, and I hope we can get more insights from other people in the community and maybe move the community a step forward here. Speaking about the community, we of course also want to thank our program committee. I won't read out all the names, but yes, they are also on the website, and a big hand to all of them who helped make this workshop a big success and help us with all the reviews. I of course also want to thank our session chairs, Katja and Stefan, who took over the 2 paper sessions. And with this, I am at the end. So that's it. That was VISGAP 2020. We hope you liked it. In the name of all my co-organizers, Christina, Guido, and Thomas, again, I want to thank you for joining VISGAP, and we hope to see you again next year. So that's it. Bye-bye.
Okay, great session, great workshop. I think we're done here, right?
Yep. Awkward silence can end.
Okay, perfect. So I'll be the first to leave.
Thank you very much for your talk.
Thanks for being here.
Thank you very much. I also leave.